Hello. Tonight, the whole of MicroLive is devoted to the microprocessor revolution in cars. Now, we'll be looking at why boxes like this one are becoming commonplace in the previously low-tech motor industry. We're starting in the highly competitive world of Formula One racing, where every hundredth of a second counts. There, the designers are increasingly turning to microelectronics to give that extra edge over their rivals. And that's why in the pit lane these days you'll find lap-held computers as well as grease guns. It's being suggested that soon, without computers, the teams won't be able to go racing at all.
This is the home of Tyrrell Racing, an elite team devoted to building cars like these. Formula One has some of the best mechanical engineering around today. It's closer to the aerospace industry than the motor trade. The body shells are incredibly strong, yet remarkably light. They hide engines which are at the center of every boy racer's dreams. Even the suspension systems are forever being refined and developed. Tyrrell are not in the business of mass production. In fact, they probably never make more than 5 of the same car. But to stay competitive, their cars have to be continually redesigned. Winning Formula One these days has as much to do with the design of the car as with the skill of the driver. The race can be won or lost on the drawing board, so you need the most up-to-date drawing board you can get. And if your sponsor is a computer company, it's natural to use one of their computer-aided design systems. We asked Bob Tyrrell why such a system is particularly valuable in his line of business.
In a Grand Prix season, we have a Grand Prix virtually every 2 weeks. And that means that there is never any time to do things. There's never enough time to design, and there's never enough time to make things. And essentially, what the CAD system allows us to do is to do things in a fraction of the time than it would normally take through traditional techniques.
Its real value is for reworking designs.
A Grand Prix car's got around 1,500 different components, and probably 70% of those we're continuously modifying during the year. And so a component that you produce, say a component in the front suspension, might be obsolete within 2 weeks of you having made it. With a CAD system, you call up the old design in the computer, have a look at it, alter some of the parameters, and you've got your new design. So it just saves a phenomenal amount of time.
Once the designs are finalized, the dimensions are passed to another computer, which controls a milling machine. It's a form of computer-aided manufacture. The design system can also be used to model vital bits of the car, like the suspension system.
What mathematical modeling really is, it's creating a mathematical description of the physical characteristics of a car or a car component. So what we're really doing is we're translating physical characteristics into mathematics, and that's, as you know, mathematics is what computers know best.
The mathematical model allows the suspension structure to be varied inside the computer and the changes in performance monitored. Here, the red lines are the lower part of the suspension wishbone, the green line the upper part, and the yellow line the axle.
Through the CAD system, you can input a model of the car or the component into the computer, and then you can then impose different forces on it. You can impose aerodynamic forces on it or physical stresses onto it, so that effectively you can see how a component reacts when you put different forces onto it. Ultimately, you always have to try out new ideas on the track. But what we're trying to do is to save the enormous time that's involved in track testing. And what the CAD system is going to enable us to do is to weed out the 90% of the ideas that are bad before we actually go and test them on the track. The ultimate objective is to simulate one of our racing cars going round Silverstone, so that we can know what the car is going to be like when we come up to the British Grand Prix. What you would need to do is to actually have a geographical model of the circuit, which would include every rise, every dip, every bump in the circuit. And ultimately, that is the way that Grand Prix car design is going to happen. We think that we're about 6 months ahead of the rest of the field, but I think you can safely say that any Formula One team that is not operating a comprehensive CAD/CAM system in the next 4 or 5 years just won't be in business.
Now, the 1.5-litre engines in these cars produce phenomenal amounts of power, and that wouldn't be possible without highly sophisticated microprocessor engine management systems. Systems which are considered so important and so secret that Renault wouldn't even let us show you what's under the bonnet. But the cost of developing and testing these systems has proved to be prohibitively expensive. So much so that certain teams have successfully lobbied the sports governing body for a change of rules next season, a change in favour of engines using brute force rather than microelectronic subtlety.
Which is ironic when you consider that many ordinary road cars are now being fitted with microelectronic engine management systems every bit as sophisticated as those on the racing cars. But before looking at the microelectronics, back to basics and how a car engine works. In a normal engine, a mixture of petrol and air is sucked in as the piston moves down the cylinder. Then the valve is closed and the mixture is compressed as the piston moves back up. The spark ignites the mixture and the resulting explosion forces the piston down again. On the final stroke, the waste gases are pushed out so the cycle can start again.
Well, the trick is to get the engine to work at its most efficient under lots of different road conditions, and that's done by adjusting the timing of the spark, that's the ignition, and the timing of the fuel injection. Now, in this car, the timings are controlled by two microprocessor-based engine management systems, one for the ignition and one for the fuel injection.
Before any new engine is even put in a car, it undergoes an extensive test program. It's subjected to a whole range of speeds and loads. And for every set of conditions, the engineers can vary the fuel mixture and the spark timings to get the optimum settings. The results are usually referred to as the engine map and the technique as engine mapping. It's this set of results, the engine map, which forms the basis of the software for the engine management system in the finished car. But before that, the map has to be checked on a prototype car on the road. This lap-held computer is connected directly to the engine management system, and it gives a constant readout of all the variables. Here, for example, we have engine speed and coolant temperature, as well as advance angle, that's the spark timing, and air-fuel ratio here. It also allows the engineers to make minor alterations, say to the ignition timing, and note the results. In this way, the engine map is constantly refined and improved.
And that set of data, the engine map, is stored in memory in the control systems as a range of settings. The memories are made up by 8x8 arrays, 64 memory locations, or 64 boxes. Each location, each box that is, can store one setting for the engine. For instance, the timing of the ignition for a particular engine speed and load. To select the best setting at any one moment, the processor checks out what's going on through a number of sensors. It senses engine speed, the load on the engine, airflow, coolant temperature, outside temperature, and what the accelerator pedal is doing. The inputs from the sensors go into the processor and are used to address the array, to look up the box with the best setting. That value is then sent out to either the fuel injection or the ignition. A classic control system, but not exactly revolutionary.
But one of the biggest problems facing the engineers was the speed of operation. Modern car engines run at thousands of revolutions per minute, so there are literally only milliseconds to process the values. To overcome the problem, the processor is selective about what it looks at. Every revolution, it has to look at the inputs which change rapidly, like the load, the engine speed, and the movement of the accelerator. And it has to send out the rapidly changing values to the ignition. The software has a fast loop to deal with these. But other inputs, such as the coolant temperature and outside temperature, only change slowly. So the processor only looks at them every now and again. A slow loop in the software deals with these. Even so, things can still go wrong. Under the bonnet of a car is a very hostile place for a micro, so the processor is designed to guard against the real world, to cope with unexpected events. And the programmers have also come up with a neat idea called the watchdog. That's an electronic timer that resets each time the software cycles around its various functions. There, it's just reset now. However, if for some reason the program hangs up, let's say it gets caught in a loop, which it will do any moment now. There. It's caught in a loop, but the watchdog timing circuitry just keeps going. And after a preset time, the watchdog switch detects that there's some problem and the whole system is reset. It's reset automatically to the top of the program. The driver would only notice a slight misfire of the engine. Now, micro owners who've tried programming in machine code and have had to turn off the machine after a program crash will appreciate the elegance of that watchdog.
Well, there's no doubt that microprocessor engine management systems do give better control. It may seem like a fairy tale, but cars can now be as much as 30% more powerful and yet have reduced fuel consumption and reduced pollution. And now, microprocessors are also being used to enhance the showroom appeal of cars. For instance, how about electrically powered seats and wing mirrors with 4 memories? In this car, you just press one button and the seat will automatically readjust itself to the position that you like to sit in. And the wing mirrors will do the same thing. In fact, there's about 9 different angles within this seat to play around with to get it absolutely comfortable. So setting it up is quite a time-consuming business. But with this, you set it up once, program it into one of the memories, and then when you want to change your car and your sitting position, it does it for you. Now, there's also on the central console, there we are, a lit-up display showing you what's going on around the car, and that acts as a warning. For instance, here it's telling me that one of the doors is open. Of course, I know one of the doors is open, but if I'd neglected to shut it properly, that would be a very useful warning. Now then, this is a very typical European answer to the problem. So to find out what's happening in Detroit, we asked Freff, our American reporter, to go and have a look and see what was going on and what they'd come up with.
And here in America, the latest in in-flight entertainment for your car is being worked on by General Motors. This little screen gives you access to just about everything, doesn't it?
Sure does. And what we have here is when you first get into the car, you have a general summary page where you can get at your basic functions such as the climate control and the radio. If you want to adjust your tone, you can go through the graphic equalizer and do all your custom sound tapering.
Okay.
How you prefer it. If you like the speakers adjusted a certain way,
to the right or to
it'll
the
do that,
rear.
or you can let the computer do it for you, and it'll center everything.
That's a nifty toy, but there's some serious stuff here too, isn't there?
Very serious. The car is constantly being monitored through the electrical systems, and you can see here we've got the diagnostic part that monitors all the major functions of the vehicle, the electrical, powertrain, brakes, and the vehicle functions, such as the door being open, the trunk being ajar.
So this will tell me if something goes wrong?
100% of the time. When something goes wrong, it'll tell you. Also, if something goes wrong and does not appear again, the computer stores it and brings it up on its own memory.
I just take it into the shop and have my mechanic call up the data.
Call it up in a second.
How many things are being monitored?
Over 100. Almost 190 different functions are being monitored constantly by the computers. It also monitors the engine as it is running, the voltmeter, the temperature.
And I see something which says trip monitor.
Got the trip monitor. That's for if you're going on a long trip or just jaunting around town. You can dial in your estimated time arrival, your distance to destination, or your time to destination. This will all be figured in for you just by dialing in the amount of miles to your destination. That's all it takes.
And it keeps track of how fast the car is moving and keeps recalculating and recalculating.
Fuel consumption, fuel economy, time of arrival, everything. All with the touch of a finger. And of course the climate control, the little fan.
I like the little fan moving around at different speeds.
It'll go with the different speeds. So it is not only functional, but very entertaining.
Entertaining, yes, but I'm not at all convinced about that touch screen. It's much easier and safer to move the controls if you can feel them, rather than having to look at the screen while you're driving. Cars like this Rover Sterling also come with anti-lock brakes, air conditioning and so on. It's all very nice, but just have a look at this. Now, you probably wouldn't feel very confident about doing your own servicing. Mind you, of course, if you owned a car like this, it could be best to leave that to the professionals. The manufacturers have produced new diagnostic instruments for their dealers' workshops, but all this is quite new to the average mechanic. It's another example of the need for retraining as part of technological change. It should be very interesting when these cars are being serviced in the backstreet garages in 5 or 6 years' time.
Well, in one sense, any car that's on the road today is already well out of date. It may be the latest thing off the production line, but already the manufacturers will be thinking ahead. And one problem they're already working on is how to cut down on the massive amount of wiring in modern cars. I mean, this is the wiring loom for the Rover Sterling. Now, these looms are expensive to make, they're difficult to fit, and soon they could literally, well, run out of room inside the body. The most likely solution will be to throw away wiring looms like these altogether and approach the problem in a totally different way.
Austin Rover and others believe that the answer is in so-called multiplex wiring. What we have here on this demonstration is the Scorpion microcontroller. It's a simple computer particularly suited for control. And attached to it, via these so-called smart chips, such as these here, are various input and output devices, such as door switches, headlights and indicators, a control panel here, and dashboard warning lights. Now, the clever bit is that all those devices are attached via a single cable, which replaces that enormous wiring loom. Despite that, you can control each device independently. For example, here I can switch on the side lights, cancel those, headlights there, and cancel, and I can switch on the right indicator and indeed the left one. There it is. Now, that's all done using a single cable, and the same cable can carry information from the car doors, for example, whether they're open or closed, and display that on the dashboard console. The system is so flexible that without any further wiring, you can tell if a bulb has failed. I'll just unscrew this, and there, it alerts you straight away. Now, the trick used to send all that information down the same line is called multiplexing. Each device on the wire has a unique address, which here we're representing by these black and red blobs. Now, this device here might operate, say, the wipers, this one the brake lights, the indicators here perhaps, and this one the headlights. Now, those devices are normally sleeping. They're only woken up when they get the correct calling address. Right, here goes the address. And you'll notice that here the addresses don't match, nor here, but here they do. So we've alerted this device, and once it's been woken up, all the data which follows will flow into this device, and that data can change the outputs. For example, the headlights might come on. All the other devices remain unchanged. That is, until they're woken up by their own specific addresses. And that's multiplexing. Well, let's have a look at a bit of the code we use to drive that Scorpion demonstration. The language itself is fairly simple. If you look at this key command here, it says net 70. Now, net is the command to talk to the network, and 70 is the address of one of the stations. Well, you can see here it says it's the right cluster, the right lights cluster. So, net 70 means wake up number 70 and take in the following. And the following is this number here, N. That number will turn on one of the lights. Well, with a controller in charge, all of those various devices could be monitored and used for, say, diagnosis or fault prevention. You could attach a printer to the same wire and pass all the accumulated data out for printing. So, as you see, it's not just a matter of switching lots of devices on and off. Using this single cable, we can control complex devices like printers, speech synthesizers, and video displays. Car manufacturers and others see multiplexing as a way of both reducing costs and increasing reliability. And we understand it won't be too long before we see it on ordinary cars.
A few weeks ago, Lotus Cars revealed this red Excel. Compared with the white standard car, there's more grip on the road and less body roll. That's because the red car is fitted with the latest version of Lotus's active suspension. As these pictures reveal, it's fitted not with normal springs and shock absorbers, but with hydraulic pistons controlled, as you might expect, by a high-speed digital computer. Well, Lotus wouldn't give us an interview, but it is common knowledge that they've been working on active suspension since the late 70s, when they were trying it out on racing cars. Lotus did admit to us that the real secret lies in the software control for the system. And it's interesting that they're working closely with a team who normally work on control systems for aeroplanes. Obviously, there must be sensors in the wheel hubs to sense wheel movement. There must be sensors to detect acceleration and braking. There must be sensors for changes in the angle of the body in all directions. We suspect there must be other sensors, but Lotus aren't saying. And Lotus are still working on the control problems. The central processor has to interpret masses of data from the sensors, decide what's happening to the car, and send appropriate messages to the hydraulics. Lotus have formed a partnership with the American high-tech company Moog. They've modified cars for several other car manufacturers, and they've been taken over by the American company General Motors. We suspect that all this must have a lot to do with the active suspension work. There's no doubt that everybody who drives the car thinks it has a terrific combination of comfort and performance. So, if Lotus can solve the remaining problems, this car may be, as one motoring journalist described it, the greatest single advance in car engineering in the last 40 years.
In America, they've been working on another problem, how to find your way about in a strange town. And one small company thinks it has the answer.
The first commercially available car navigation system in the States is something called ETAC. Now, the name's peculiar, but it makes sense. It's named after a Polynesian navigation technique. They used to get into their canoes and set off between the islands and assume that the canoe was stationary, but that the islands were moving past them. And that's how ETAC works. On the screen, you have a cursor which represents the car, and it orients itself the same way you do, looking through the windscreen, and the map moves around you. Let's take a look. I'm driving along a curved road called Kennedy in the back of an industrial park in Detroit, about to enter deepest American suburbia. And you notice that the map keeps its orientation with the car. The view on the map is exactly the same as the view looking straight through my windshield. So as I go around the road curves on the map. Now, ETAC works with 3 different sensing systems. There's an electronic compass, which is always telling you north, south, east, west. There are sensors in the wheels, which tell you what direction you're moving and keep track of the revolutions of the wheel so it knows how far the car has traveled. That's the dead reckoning system. Take that and the compass and the map data and put them together, and ETAC can make corrections for its errors. Coming up on an intersection called it's Kennedy and Common. If I make a right turn here, let's see what happens. There's a potential error of about 50 feet in the dead reckoning method. So it self-corrects constantly by keeping track of where you are on the map. If you turn on to Common, and it knows it, it automatically snaps the arrow dead onto that street. So what ETAC does is as you come up on intersections, as you make turns from left to right, it compares the turn you're making to the map data and makes its most sensible guess. Most of the time, it's a right-on. A little earlier, I drove down one street. It thought I was on a one-way street that was right next to it. But when I drove clearly past the end of the one-way street, it knew that an error had been made and put me back on my right course. According to the map, I'm coming up on Lorraine, and indeed, Lorraine Boulevard it is. You'll notice that the arrow is not actually on Common, but as I turn onto Lorraine, it knows that's the only street I could have turned onto at this point, and it'll lock me back in, correcting for the error in the dead reckoning system. And there I am proceeding along Lorraine. You're offered a number of scale views, which are accessible by soft switches. Each of the buttons along the side, and there are 12 of them, access soft switches. They change meaning depending on what screen you're in. Across the top we have our scale, an arrow pointing in the direction of my selected goal, and a little number which tells me I'm 0.6 of a mile from it. Also, you have an indicator for the actual direction of north at the moment. Over on the right, we can choose to look at it on different scales. You can get a big overview of the whole town, in fact, of half the state, or you can go back down to the neighborhood look, which is where we are. The way it works is you enter a destination. My destination has been entered but isn't visible on a map this size. You can see it on this size as that flashing star there. And I know if I continue on this up to 13 Mile Road, turn left, it'll get me where I want to go. Important to ETAC's future success is that General Motors expects to build the system into their cars in a year or so's time. At GM's Technical Center, Ron Jameson showed me the sensors which need to be fitted to every car. 2 of the wheels have a magnetic strip on the rim. As the wheels rotate, this sensor generates electrical pulses which are compared with the pulses from the other wheel. In case the wheels have slipped, the computer also consults the electronic compass. On this car, the compass is in a sealed box in the boot, along with the electronics for the system. and the digitized maps are held on data cassettes which run on a player with a special high-speed drive. Why did GM choose ETAC over other navigation systems?
There were several systems that were looked at by GM, but ETAC was the most technically advanced at the time we looked at them and seemed to have the most promise.
All right. What about satellite systems?
General Motors has looked at satellite systems, and presently there is a satellite navigating vehicle around. The problem with the satellite system right now is not all the satellites are in space to support the system, and the plans to do that have been slightly delayed. Also, a satellite system represents a much more complex system because of the receiver that has to communicate with the satellite. And in addition to that type of interface, you still need to have the map base and compare position to the map, so you're doing the same types of things that you do with the ETAC system.
Essentially, a satellite system is not only more costly, it's a lot of stuff on top of ETAC is what it is.
Exactly.
Well, some idea about what might be coming next can be obtained from this, the Prometheus report. It's a study on the long-term future of information technology and transport. In one sense, at least, it's unique. It's been produced by several European car manufacturers working together. It suggests that by giving drivers extra help, motoring will become safer and traffic will flow quicker. It says that human factors like inexperience, uncertainty, limited vision and slow reactions need no longer be the cause of accidents. For instance, systems at the roadside might integrate with the in-car navigation systems we saw earlier. The driver could receive information about warning signs, traffic jams, or even the location of parking places or petrol stations. Cars could be fitted with systems which could detect the presence of other vehicles, even in heavy rain or fog when the human driver couldn't see. And the report goes much further. It suggests the installation of expert systems to manage this information. For instance, the expert system might be programmed to maintain a fixed distance between cars. Then cars could travel very close together and gain the advantage of slipstreaming. Motorways could be very interesting places. We could be seeing a move away from the car as a personal means of transport and towards a car as a unit in an integrated transport system. Driving would certainly never be the same again. If this report were to be taken up in any serious way, it would bring together manufacturers in several different countries, which in the long run could do wonders to the European IT industry.
Well, cars haven't really changed all that much over the years. They're mostly still, they mostly have petrol engines, they've got a body and four wheels, but perhaps today we are seeing the start of a revolution. Perhaps the microprocessor-based developments of today and tomorrow are going to change cars beyond recognition.
Well, next week, we'll be looking at the fastest growing use of micros for electronic mail. Now, if you're already using email, we'd like to hear from you. These are the special mailbox numbers to call up. Tell us, in not more than 100 words, please, what you use electronic mail for and whether you have any serious criticisms of the system. Well, that's next week. So, until then, good night.